Welcome to another episode of the AI in Manufacturing podcast here on Industry 4.0 TV. I'm your host, Kudzai Manditereza. On this episode, we're going to discuss reinforcement learning and AI agents for optimizing industrial plants. My guest on this episode is Kyrill Schmid, who is the lead AI engineer at Mybonhof and also the co-founder of Zen AI. Kyrill, it's a great pleasure to have you on here.
Yeah, thank you very much, Kudzai, for having me. It's a pleasure to be here.
Oh, yeah, absolutely. I'm really looking forward to our discussion today. But before we jump into the discussion here, could you introduce yourself to our audience? Tell us a bit more about Mybonhof, your role at the company.
Mm-hmm. Yeah, sure. My name is Kyrill. I started actually working with machine learning and deep learning and autonomous agents a couple of years ago. So actually, before the current AI boom, around 10 years ago. So during my PhD at this time at LMU, I used techniques from machine learning like reinforcement learning to do optimization problems within production and manufacturing settings. And then after finishing my PhD, I worked around 2 years as a trainer, as a machine learning trainer for companies, more for IT companies who want to embrace and adopt machine learning things in their companies. And then I joined Mybonhof last year, in the beginning of last year, and there I'm part of the data and AI team. And yeah, currently a lot of things are around LLMs, especially since ChatGPT. But also we have a tradition in more classical data and machine learning applications. So we help our customers build become data-driven organizations and use data for various use cases, analytical use cases, and also currently a lot of things around LLMs and this stuff.
Oh yeah, absolutely. I mean, it's really interesting, that you've got, a background on reinforcement learning, as you mentioned, throughout your research. And what we're seeing increasingly is the application of reinforcement learning to power AI agents, like in many industries, but more interestingly for industrial plant optimization. So maybe to start here, could you explain briefly what reinforcement learning is, and also kind of like talk to us about how it relates to AI agents or modern AI agents, particularly for our audience here who may be familiar with your normal predictive AI and things like that.
Mm-hmm. Yeah, so sure. So reinforcement learning is quite a framework which goes back into the 90s or maybe even longer. So it's a sort of a learning framework. Um, and it's somehow different than what we know from nowadays AI, what we call nowadays AI. So it's mainly about goal-oriented learning. So in the center of reinforcement learning, there's also the term of an agent. So the agent is really the entity who tries to reach a specific goal. So you have the agent, and the agent is within a specific environment. The agent can act upon this environment by doing specific actions. So this is the next thing. So you have an agent, you have an environment, and the agent can observe the environment and observe what its current actions do to the environment. And so the agent's goal is to find a strategy, also called a policy, to maximize a specific goal or to reach a specific goal. And so you have a fourth thing within the framework, which is a reward function. So this is the actual signal the agent tries to optimize and to learn from. So you can think of, to make it more illustrative, you can think of an agent, for example, who tries to learn a specific game like chess. And then the agent starts playing chess, and just by repeatedly and doing trial and error and trying different actions, the agent over time would learn what are the impacts of specific actions in specific states. And then you can also signal the agent when it has done well, so by seeing that it has won the game. And this is how the agent over time would learn to find an optimal strategy within this environment.
Yeah, absolutely. So, I mean, in this case, do you see, or is there a link between the reinforcement learning agent and the the more recent definition of an agent, where you have got like an LLM at the center of it all? How do these sort of like two work hand in hand?
Okay, yeah. So first of all, the term of an agent. So nowadays we use AI agent as a term, and what we nowadays mean is like an agent built upon an LLM, so a large language model. So and the agent is a classical term within AI or learning. So what it means is there is an agent with an open-ended task, and the agent can act in some way so that the task is open-ended, and it tries to adapt and find ways to solve a specific goal. And this is in the center of it. So this is an agent. Nowadays, as I said, we leverage LLMs to do intelligent things within or for a specific task. But with reinforcement learning, we would also have a specific learning process. So the agent really is doing some sort of trial and error. So it really applies actions in order to see what the impacts are, and then learns upon this. So this is different from what we have nowadays with LLMs. So with an LLM as an agent, we would say the agent already has a lot of knowledge because of the pre-training that it has been gone through. And so the agent wouldn't learn on the fly while doing specific things. So this is maybe the difference.
Oh, I see. All right. So maybe because that's such a powerful approach to solving problems. So as you may know, in traditional industrial control systems, you have a situation whereby the control logic is really something that is hard coded on a PLC. Some plants right now are running with control logic that was developed maybe 20, 30 years ago, right? It doesn't really change, and maybe you may only just have like a process engineer kind of like working hand in hand with that rigid logic to sort of like try and solve problems whenever they sort of like come into a challenge, and which makes it really difficult to solve complex problems, right? Because there's just so much, as you said, path to try out and see what could have been the cause of this specific problem, or what's the optimal way of, say, maybe saving some energy or becoming more energy efficient. So I wanted to get your sense on what, in your view, makes reinforcement learning more sort of like suitable for these complex industrial challenges.
Mm-hmm. Yeah, so maybe that there might be some limitations to traditional control. So as you said, so for we have maybe systems with high degrees of complexity and also maybe degrees of non-linearity. So maybe with traditional control, we can do specific things really good, but maybe they do not scale in the numbers of variables that we want to consider for specific problems. And also traditional control might be in its nature static. So we have like controllers, hard-coded controllers that do specific things really well, but they are statically, so they will not adapt to changes within the environment. And so I guess what reinforcement learning could provide additionally, so not by directly substituting traditional control systems, which might be working really well for specific domains. But reinforcement learning might be like a sort of additional layer of optimization for specific problems. So, for example, for problems where we do not necessarily see all the correlations between specific variables. So we can really tackle high-dimensional optimization problems with reinforcement learning, and also optimization problems which are like sort of developing or changing over time. So an agent, continuously learning and adapting agent may be capable of adapting to a changing environment, right? So we are always going on, and we observe things like data drift and all that, and continuously learning agent may be able to adapt to those changes. So these are some of the things, I guess, reinforcement learning agents can additionally provide as a complementary thing to traditional control systems. And also, there are specific things also from, I would say, from a more technological point of view. So reinforcement learning per se does not describe a specific technology for learning. So since a couple of years, maybe 15 years now, we can use deep neural networks at the center of reinforcement learning as well, which allows us to deal with really high dimensional domains and state spaces and action spaces. So this is something important. And yeah, we can optimize, for example, to give another example, we can optimize for long-term goals. So an agent, as I said, will apply a sequence of actions and go through a sequence of states. And by repeatedly doing this, it might find completely new ways to solve a specific optimization, or to find solutions for specific problems, which we humans might not even see. So there is a famous paper that came out a few years ago, which not directly only uses reinforcement learning, but also relies on reinforcement learning ideas. And there they tried to solve Go, which is a famous board game, especially in the Asian region. And it's really complex because it has a lot of states, and then they really sort of trained reinforcement learning agent on that. And after, what they observed is that this agent in the end really found completely new solutions within the board game. So these were solutions and strategies that we humans didn't even were aware of. So first people thought like, okay, what is the agent actually doing? And then they found out that these were completely new strategies. And in the end, the agent now is the most capable Go player. So it won against the currently world champion in this game, I guess 100 times. And so, this is for really narrow and specific domain, but with completely new solutions.
That's really super interesting what you mentioned about this idea of the agent being able to discover all those things that you may not know about, right? Which really I think works perfectly in a manufacturing setting. Again, to use the example of energy efficiency monitoring, there's so many variables that you may not be aware of that are kind of like causing that could lead to more efficient energy usage. So you also mentioned kind of like at the beginning of this talk that reinforcement learning may not be suitable for some use cases where you kind of like have your traditional AI. Could you kind of like give us a picture of what examples would work best for like your traditional predictive machine learning AI, and maybe an example of what would work best for reinforcement learning?
Okay. Yeah. So maybe to give there also a bit of context. So I guess what we saw in production and manufacturing field, and this were more like traditional machine learning applications, like sort of prediction tasks. Like for example, let's call the one thing predictive AI. This is more like we train a specific model. Oftentimes we do have like a static or already known data set. So for example, typical examples are classification, or also regression problems where you try to predict a specific number. So for example, what would be the energy consumption of my plant tomorrow at this time? So this would be a regression problem. Other things are more like classification problems, like you want to classify specific states. So these, what we nowadays term as traditional applications of AI, these are more like analytical things. So we want to use machine learning in order to provide information towards other systems or to humans, to underpin or to help making better decisions at specific points. So really like narrow scoped. You have a specific problem and you train a specific model based on data that you have to provide the missing piece. This is what we nowadays call traditional machine learning, or AI. And with I would say the difference with reinforcement learning is that you naturally have like you do not have like so there are different dimensions that you could try to find differences or mark differences. So the first thing is the goal. You do not necessarily try to predict a specific number or to classify a specific state with reinforcement learning, but you really have like an open-ended task. So you have an agent, you can think of control tasks like moving a robot. You can also think of other control tasks like change the parameters of a specific controller to optimize for energy efficiency and all that. So it's open-ended, and it also has this temporal dimension. So the agent does an action in a specific state at a specific time, and it then moves through time and a state space. It has differences also in terms of what data you require. So for classical machine learning, normally you would before you could do something, you need to collect data. For classification tasks, that would mean actually you need data, and you also need to label data in order to train a model on it. And with reinforcement learning, this is not necessarily the case. So with reinforcement learning, you really would do like online, for example, you could do online training. So the agent acts with its environment, and while it's doing this loop, it collects data on which it then learns. So you need not necessarily gather data beforehand. This also makes it challenging because this data that the agent collects is not independently distributed. So the action that an agent chooses in a specific situation will determine the future states, and also the future states that the agent will come to in the future. So this means that you have dependencies between your data traces, and this makes learning more challenging, because then you can come into, you need to make sure that you get a broad picture of the data distribution that you have. So it's really in terms of training a model, reinforcement learning is often more challenging than training traditional machine learning models. So the learning process is fundamentally different. Yeah, and so as I said, especially the output is a difference. So for predictive model, that outputs, for example, a forecast or a classification, and this could be a typical outcome of such a training process. And for reinforcement learning, it would be what we call a strategy or policy that does something useful in a specific state. Yeah. So these are maybe the differences that for.
Yeah, that's interesting. I guess maybe I would like to sort of like linger on that topic a bit to get your sense on what, because it sounds to me like you said, the reinforcement learning doesn't necessarily have that traditional data, preparation, to then train a predictive model and things like that. Uh, but I would imagine it still needs to access high quality data
Mhm.
as it kind of like explores. So, maybe if you've got some wrongly calibrated instruments, it will learn the wrong things, or it may not get a good intuition. So maybe my question here is to say, what about the data needs to be perfect, or needs to be, you know, correct, so that the reinforcement learning could really be effective? What aspects of data need to be, really paid attention to?
Yeah. So I would say, while for um, predictive AI tasks, we typically have this issue of we need to collect data beforehand, and this normally needs to be in really high quality to allow a model to train on. The data requirements for reinforcement learning are different. So there are two categories of learning. So the one category is called online reinforcement learning. This involves the process as I described before. So you have an agent that interacts with its environment. The environment could be also a simulation of the environment or a trained model from the environment, but the agent really needs to interact with it to actually learn. There's another approach towards reinforcement learning that relies on the so-called offline reinforcement learning. And there you have the data already at hand. So maybe you have from specific systems like a SCADA system or some operational data that you might use in order to train an agent on. So you have already data collected, and then you can train the agent afterwards. This is a bit more, might be more handy in manufacturing, because you might have data from historians or whatever, so that you might want to use. And maybe you do not have a simulation that you can put directly with for online learning. But for offline reinforcement learning, there are other challenges. So you need to have a really broad distribution of data, not only specific data points. So because if you want to train an reinforcement learning agent, the goal is to find an optimal policy. And if you only provide a narrowly distributed stream of data, then the agent cannot explore new and good ways to solve it. So you need to make sure that the data that you have is really broadly distributed in this state action space. So these would be the minimal requirements: either have data in place or have a good simulation, or like an environment that you can really leverage for online reinforcement learning.
Oh, yeah.
Yeah.
Yeah, that's actually a good point, and also a segue to my next question, where I've seen some approaches where companies use digital twins. They create a digital twin of a plant,
Mhm.
of a of a piece of a machine, which is effectively a simulation that you're referring to, and then sort of like use that as the training ground for the reinforcement learning agent, so that it could learn before it is deployed in a real environment. What do you think about that approach?
I would say there are a few points that are that could be an advantage in that case, if you have a really high fidelity sort of model or digital twin that you can build upon. First thing is that it allows you to safely explore, right? So an agent really needs to apply actions and see its consequences. So if you have like an actuated system or robot, you wouldn't want to let the agent actually control this robot and run against the wall or fly a helicopter or optimize your energy in the plant, in the field, because this could lead to catastrophic situations and really costly situations, and also situations that are maybe dangerous for humans. So having a simulation allows you to explore the whole state space safely. This is the first and most important benefit. Another benefit would be that you, with a simulation, you can use all the advantages of compute. So you can do simulation faster than real time, which is an advantage because with reinforcement learning, you typically need a lot of samples. So you need a lot of transitions of state actions to the next state in order to let the agent learn. So it's really data hungry in the end. And you can increase the speed of your simulations, right? So you can do years and years in a few hours or maybe a few days of simulation. And you also can parallelize it. So you can, if you have a simulation, you can set up hundreds of simulations in parallel and train the agent and all this massive data amount that it's coming. So it brings a lot of different advantages to have a good simulation, especially for reinforcement learning training.
For someone who's listening to this conversation and they're thinking about maybe we wanna try and deploy this or sort of like start experimenting with reinforcement learning, could you paint a picture for us on what are the essential pieces of infrastructure that would be required to sort of like implement reinforcement learning agent? Kind of like, can you kind of like talk to us about that stack? What does that look like, and any necessary hardware requirements for that?
Mm-hmm. Yeah. So I guess overall you need to at least think about 3 layers of infrastructure that you need. So the first is the maybe data dimension. So as I said, you need a you wouldn't necessarily need so you need sort of a data generation process, be it a simulation, be it data that you already acquired during or that you have. So data coming from your SCADA systems, from your operational systems that you can leverage. This typically would also involve then like setting up data pipelines to bring the data into the actual training process. So you might be also need specific connectivity and protocols to support the training process, because training a reinforcement learning agent typically needs a lot of compute as well. So what we do when we do like sort of deep learning agents, or really an agent that is built upon deep neural networks, you have a lot of tensor operations. So these are multidimensional matrices that you compute. These are typically best supported by GPUs, which have thousands of cores that you can parallelize these operations on, or TPUs, which are dedicated specific hardware from Google to support this. And you need I guess the challenge is to bring the data from various systems, especially now in production field, which might be coming from OT systems, SCADA systems, historians, to bring this into the dedicated training environment to parallelize this. So as I said, so you need data, you need the connectivity and the protocols. So SCADA systems, or also things like MQTT and UNS might be helpful protocols to support training. And of course it needs and a lot of data management and processing management around to actually allow for efficient training.
Yeah, absolutely. Yeah, I mean, so you obviously, in your role at MyBonhof, you obviously interact with some, customers as far as, AI, implementation is concerned. So both industrial and other sectors. I want to get a sense from your end on, particularly on the industrial side, what is the level of maturity? Do you think companies are ready to implement advanced technologies like reinforcement learning? And if not, what are the the steps that are still required, whether it's maybe the cultural shift, the skills shortage? What to you is kind of like your assessment?
Yes, I guess from my personal perspective, it's oftentimes it's really the the data infrastructure. So this is oftentimes the first thing that needs to be built. So to allow for these machine learning use cases, in the end, it's the first thing which often is not in place is appropriate data structure, data infrastructure. So especially in production manufacturing, where we have a long history of infrastructure that we build upon. So production sites that are built tens of years ago, and which are also built to be there for at least 30, 40, 50 years. So there are some oftentimes systems where we not directly can leverage data. So it would typically need a lot of data engineering before we can really build upon. So there are things coming up, like as I said, for example, the MQTT protocol and UNS to sort of solve this problem, but is typically the first thing that you mentioned. And then other things are, of course, so as I described, so reinforcement learning in itself is quite challenging due to the specific things that you need to be aware of. So you need the specific skills to set up such a training process. You need also the infrastructure to actually have the right amount of compute to actually do it then. Typically training and reinforcement learning is something that is compute and time intensive. So you need to have the right people and the right computing infrastructure to actually then also do it.
Oh yeah, absolutely. Yeah, I mean, the other thing that I wanted to get your take on is this idea of I mean, as you mentioned, fundamentally, this is still, deep neural networks, right? Meaning that this is still very much a black box, all the decisions that happen inside there, which may be fine in situations where you are training it to play Go. So maybe you don't really, worry much about why it took the decision that it took, or maybe in some other situations. But in high stakes environments such as manufacturing, you wanna always have some form of reasoning
Mm-hmm.
to say why, kind of like, for it to gain trust, it should be able to indicate that it knows what it is doing. It took the certain decision because of A, B, C, and D.
Mm-hmm.
Is there any way that you could get insights into how reinforcement learning is making decisions, and how do you trust a black box system?
Mm-hmm. Yeah, again, here I would say there are multiple dimensions where we can act to improve trust in these systems. So as the first dimension, as you said, would also be for me to make it or to provide better transparency and explainability. There are different techniques within machine learning because, as you said, at the center of an agent, we have a deep neural network. So this is in essence only a set of numerical parameters which we cannot directly have a look into and see why decisions were made. So some input goes in, some output comes out, but why, it's not clear. So it's just trained upon data. So there are different techniques to make it still a bit more or a bit better explainable and to have a look into the black box. For example, you can sort of for example, do a visual highlighting of what are specific inputs that drive a specific output. So this could be a first way of making it more transparent, so that also human operators or managers see, okay, the agent has done a specific decision because of this feature input that has gone into it. So there are different techniques within machine learning to directly support this. I would say another dimension to improve trust in these systems is reliability and performance. So when we frequently evaluate systems and when we have specific KPIs in place that allow us to control what are the current outcomes, what are the things that in terms of performance the agent really does. It also helps to build trust, even if we cannot directly have a look into the black box, but it helps to make it more transparent, I guess.
Oh yeah, absolutely. So when we talk about trustworthy AI, or rather more of an AI that acts as an augmentation for decisions on the shop floor, is there a way where you could have, does reinforcement learning, is it always a closed loop, or is there a possibility for a reinforcement learning agent to hand over decision to like a human, and then it
Yeah.
continues?
Mhm.
Is that a possibility?
Yeah, this is possible. So this is possible in two stages. So it's possible during training. So this often even helps to provide better or stronger policies. There's a really illustrative example of that, of a robot doing backflips, and it's trying to learn backflips, and it's really having a hard time, because it's not easy by just, so you need to imagine, so you need to actuate a body with different degrees of freedom in all joints. So and how do you, so the goal is to make a backflip, and by just applying random actions, it's not really probable or likely that you will do a backflip at any time, because you need to try so many different actions. And in these kind of situations, it might be helpful to do a specific, to follow a specific training paradigm, which is called imitation learning. So in this case, for example, a human expert might guide the learning agent towards better states. So it identifies, okay, if you do this or follow this policy that I give you already, and you will faster or more quickly come towards a desired state. So this is during training, where a human or human expert or another expert system could provide specific feedback to improve learning. And also during inference. So if you have trained a policy, you still might want that at any point of time for control systems, a human might be able to intervene. So having a human in the loop for specific decisions, or also being capable of escalating situations towards a human is something that we should aim for most systems, I guess.
Oh yeah, absolutely. Cool stuff. So I mean, another really critical issue when it comes to AI implementation in industrial environments, or in any environment for that matter, is the issue of scalability, right? Because a whole lot of manufacturers have got this problem where you could maybe, for example, have got a reinforcement learning agent that has learned how to optimize energy efficiency of a maybe of a chiller or some
Mhm.
piece of equipment. How do you scale that out to all the chillers across your entire plant, or to other pieces of equipment that may not behave like a chiller? Does it mean you need to train separately for each piece of equipment? How, I guess my question is, how easy or difficult is it to scale reinforcement learning across a manufacturing enterprise?
Mhm. Yeah, I guess it's not an easy one to scale things across a complete or an organization. Um, because it has there are points you need to be aware of. So the first thing is, I guess, maybe model generalization versus retraining, because you train for a specific state, or you train for maybe a specific production line, and to generalize across other production lines might not be directly supported. So what you might think of as a potential solution is like a similar approach that we are currently doing with large language models. So you have like a really huge a huge model pre-trained on a really diverse set of data. So this is our GPT-4, 5, or whatever. And then you sort of use this base model to fine-tune specific models for more narrow cases. So this might be a way for large enterprise situations to to customize for specific things, like having a huge base model and then do fine-tuning for specific sort of stuff. Then of course you need to make sure that you like centrally be able to have all the data infrastructure in place to manage data centrally, to make data accessible as an organization. Also, this is important. And in the end, I guess it's also a lot about not only technology but also about change and socio-technology change. So we also cannot we cannot think that we provide a technical solution and change an organization just by that. We always need to bring the human into the loop, and we need to build trust, as you said, and we need to make sure that people who are working nowadays leverage the technology that they get. So this is also a change process that we need to be aware. If we change organizations, then we always change people as well. Need to talk about changing people as well.
Yeah, absolutely. Yeah, I mean, as a tradition, I like to ask our guests to give us a prediction on where they see AI in manufacturing, or how they see AI impacting manufacturing in the next few years. So what is your your view on where things are going? What does that picture look like for you with AI in manufacturing?
I guess it will kind of lead to a renaissance of AI in manufacturing. The ChatGPT and LLM thing will kind of trigger this, because now companies get aware that bringing their infrastructure and their setup in place, companies are doing this right now. And the next thing, I guess, after having this boom around LLMs, will be to look into more of those large scale optimization problems in production sites. And I guess they will become more also these techniques, which are nowadays quite challenging to realize, will become more accessible due to AI, because what we observe within software engineering, but also specific domains like machine learning, so we really can leverage AI in order to build this stuff. So it will be easier to access. It will be maybe also not that expensive anymore. So I guess this will really create a boom of AI in for example, production to come in the next years to come.
Oh yeah, absolutely. Kyrill, we've run out of time, but before I let you go, just quick last thoughts. So we're going to provide links to your LinkedIn and also to website for Meibenhof. But any last words for our audience? Where can they find you? Do you have like any interesting content that they should check out? How do they get in touch with you, or how do they sort of like partner with Meibenhof as far as AI is concerned?
Yeah, so I'm located in Munich. So if you are around, just write me a message. This is the easiest way would be to just reach out on LinkedIn. So there I'm easily you will find me easily there. Just reach out. Also for online chat or whatever. So if you are specifically interested in artificial intelligence or machine learning, specifically in production, but also in other domains, reach out and we can have a chat at any time. So it would be great to have a few reach outs there.
Absolutely. So Kyrill, thank you so much again for taking the time to share your insights with our audience today. I really appreciate it.
Yeah, thank you too, Kudzai, for having me. Really, really cool talk. Thank you.